So this is the afternoon for the discussion of theoretical computer science in general, and that's fine. And discrete mathematics. I'm going to have some preliminary remarks. That's interesting. I'm going to have some preliminary remarks, mainly about computer science. And later on, I think my voice is strong enough, isn't it? It won't be recorded. The golden words. Okay. So, now I am confused. I'm going to devote some opening remarks to computer science, as I said. Then in the course of the discussion, we'll also ask people to make some comments about discrete mathematics. And all of that is going to be intertwined with, I hope, a lively and productive discussion. I would like to start by giving you some kind of a morphology and very brief history of theoretical computer science. And that can serve as a background to what we'll say on that topic, and illustrating also various points. So computer science is really an example of the process that people looked to and hoped to have in mathematics, looking towards the future. Namely, in the 50s, the computer technology, this whole field arose, and at the same time, concurrently, and in fact even before, and you'll see the antecedents, a theory of computing was developed. And the relation, this is a kind of applied mathematics, and in the same way that a certain kind of mathematics, mainly continuous mathematics, was developed in order to deal with physical phenomena, mainly, let us say, in the beginning in classical physics, phenomena of mechanics and electricity and magnetism. Now the process of computing itself became a subject of mathematical study with some very useful and very influential results. So we really see here a new branch of applied mathematics. So speaking about some of the history and some of the achievements, the notion of computability itself was already introduced in 1935 with the work of Turing, Gödel, Church, and it was one of the foundations later on of computer technology. And then also concurrently and going into the 1950s, late 1950s, and even beyond, various kinds of mathematical machines were defined. The best known are the Turing machines that had, and this is an historical fact, had a profound influence on the architecture of modern computers. There is a direct link between these two, but also other machines may be less well known, for example, finite automata, so-called push-down store automata, which have a great significance both in linguistics, in the Chomskyan theory of linguistics, and also in programming languages, and actually play even a big role in the technology of, for example, compilation of programming languages. So these abstract machines, there is again a direct link here between the theory and very important applications. Now, around 1958, let us say, computability and its mirror image, undecidability, was well understood, not just in logic, also in algebra and other fields. There were even undecidability results in topology, for example, Markov. And now a finer analysis of the realm of computable functions, i.e. in principle computable functions, was introduced, namely the computable functions in 1958, starting with 1958, were classified according to the difficulty of their computation, the inherent difficulty of their computation. So computational tasks were a spectrum of solvable problems was introduced. Now, I mention on purpose the name first given to the field, difficulty of computation, rather than complexity, because in a sense it is more appropriate. It talks about what you are really concerned with, namely the difficulty. You see, complexity, and I'll come back to that topic later. Complexity deals with systems which are very, very complex in terms of having many components, and especially interacting components and feedback mechanisms. So, for example, global climate is a complex system. Now, the difficulty of computations problems actually relate to very simple objects, a number which is a product of two primes. How difficult is it to factor? A question of cardinal importance. But the name complexity sort of caught on. It's more sexy, so that's what we have now. And this started in 1958, is open. Now we come, in a sense, to the practice. All that deals with the study of the computational process as an object, as material. Now we are sort of sliding also into the applications. And this is the vast field of efficient algorithms. Starting, and here I'm a little bit maybe ignorant of exact dates, starting with Euclid's algorithm, which I sort of randomly assigned the 200 BC date. Who knows when Euclid lived? And going into the present. And the salient point of efficient algorithms is, and Euclid's algorithm is an outstanding example of that. You would assume from the definition of the greatest common divisor that you would need to know how to factor in order to compute, if you just look at the definition. And we know that even today, in 1999, factorization is a hard problem. And cryptographers will say, thanks heaven. So, but he had a way, as we know, and it's, we could call it trivial, with hindsight, he had a way of very efficiently calculating greatest common divisors. And these efficient algorithms which touch every aspect of computing, whether these are efficient algorithms in number theory, in algebraic questions, in combinatorics, graph theory, what have you, languages, everywhere, data structures, which I'll mention further on, fast Fourier transform, signal processing, etc. These are, many are intellectual gems in their own right, and many of those are also of the utmost practical significance. Within efficient algorithms, there was the big surprise starting in 1975 that randomness, tossing coins, can be used to solve problems which before that and even now are inaccessible. That was really an enormous surprise. And in many areas, randomness, for example, in protocols for security and other applications, randomness, in fact, is essential. There is a sharp distinction between randomization as used within algorithms and even though people use the name Monte Carlo and Monte Carlo methods, because in the Monte Carlo method, for example, in order to solve a potential equation or a diffusion equation, you create a a stochastic process that imitates, that behaves according to the equation that you are trying to solve, and then you perform very large-scale experimentation. They are characterized by the use of many, many random bits. The randomized algorithms are very, very sparing in the number of bits that they use, and they produce just outstanding results. Starting in 1971, and no, 75 it says, and that's correct. Starting in 1975, modern cryptography started with the work of, with the proposal of Hellman and Diffie to use public key, which I've explained in my lecture on cryptography, and those who had the bad fortune of missing it can ask others what that is. And but they had another very interesting point, which is sort of not explicitly stated in what they say. They proposed using well-known mathematical functions and problems as basis for cryptography. The cryptographic devices prior to that, such as the Enigma machine and the data encryption standard, these were some hodgepodge of boxes and processes which did not provide you with any clear picture of what was going on. And they first made the proposal, Diffie and Hellman, to use discrete log, and then came the proposal to use the difficulty or the presumed difficulty of factorization as the basis for cryptography. And then there are now proposals of using various lattice shortest vector in lattice problems, etc. But the proposal to relate cryptography to well-known mathematical problems is actually implicit, maybe even explicit, in their paper. Now, cryptography, as I was explaining, is not only the creation of secret codes, but is really the whole issue of having protocols, which is at least as important as the secret codes. And all of electronic commerce, all of internet work and so on is actually dependent on and will be dependent on that technology, both on the secret codes and even more so on protocols. And all of that field has a very, very nice mathematical structure. Now, then one should mention, even though this is in some sense subsumed under algorithms, one should highlight data structures, and especially very large data structures. So we know, and it is obvious, that modern life is dependent on extremely large so-called databases, what you have in the banks, in, God forbid, Internal Revenue Service, medical records, all these web pages, all that data which is floating around and that is organized, and to access that data, search that data, data mine it, and so on. All of that depends on an understanding and on efficient algorithms for data structure. That is a whole field which is, again, mathematical, combinatorial in nature, and at the same time, and even before, yes, is of essential practical importance and significance. Then, so let me talk about the other component of the modern communications plus computation complex, namely networks. So we have, this is called the internet, but I'm talking about the underlying technology. So there are these enormous heterogeneous networks. And here there is a need for real understanding. And again, these are one of these very complex systems in the sense of actual complexity, not complexity theory, but systems which have millions of components and where a real theory and deeper understanding is required in order to bring feasibility and practicality. Let me mention to you one of the issues that is involved. We are all familiar with the frustration of trying to get something over the internet and the delays that result. Now, the delays are not a consequence mainly of the communication lines. The lines have very high so-called bandwidth, and that bandwidth will greatly increase with sophisticated fiber optics, what have you. The problem is, what is happening in the internet is that this data, think about it as pages, is hopping from one node to another node. There isn't a direct connection created between you, a wire that directly plugs you into the database from which you want to draw the information. But it is hopping from node to node to node. And in those nodes you have so-called, I hope I'm not becoming too down to earth for people here, especially after lunch. But in those nodes you have buffers. So obviously you need temporary storage where those pages sit while they are being moved and while decisions are made how to route them further. And the failures are buffer overflows. Now, we used to, in telephony, we used to consider questions of loads in terms of Markov processes. This is, and that's how the telephone people were able to provide sufficient bandwidth or whatever, and also switching in order to route telephone conversations. This situation is much more complex, among other things, because of feedback phenomena. Namely, if you fail to get the page, then you are immediately asking for the same page again, or maybe the system itself generates the same page, sending it in the same or maybe a different route. So usually these catastrophes are self-compounding, and we don't have understanding of these processes. And here we have to talk about two facets of this. First of all, a better understanding of the stochastic processes involved here, and then also mathematical, not technical inventiveness. How to do that routing, and again, randomization and ideas of randomization obviously come in. How to do that routing in a way that smooths out those loads. And that is a very active and by no means completely understood area. So that's another example. Now, my list is by no means comprehensive, but I want to mention parallel and distributed systems, and again, the mathematical problems associated with these. So, of course, people build parallel computers, but the idea of parallelism is clear, that even though we have very powerful processors, very large memories, and so on, the needs of very large-scale computations, the needs or the consumption of instructions is so prodigious, for example, if you want to do weather prediction, that a single processor is not going to do it. And the idea is to harness together hundreds or maybe thousands of processors in order to, in unison, solve this big problem. Now, this cannot be done pragmatically. In fact, theory had a profound influence on the technology of parallelism in several ways. So first of all, there were pure mathematical theorems, and I'll mention only one of those just for your enjoyment. A theorem which has essentially no practical application, but is just intellectually attractive. Namely, consider the task of calculating, say, the determinant of a very, very large system of equations, and not sparse. say 10,000 equations, 100,000 equations in 100,000 variables. Now there are things like that that arise. Now if you think about the way we know how to do it, then say Gaussian elimination, there are other methods, but say Gaussian elimination in a sense is fairly eminently sequential. You can somewhat parallelize it. It's an ugly name, but it's being used term. You can somewhat parallelize it by while you are subtracting multiples of the first row from the second and the third and so on, you can have several processors work on it together. But a surprising theorem due to, who is it, Kachin? No. Pardon me? Chansky, yes, Chansky. A surprising theorem due to Chansky says that you can do it in parallel if the matrix is n by n. Using many processors, you can do it in time log n squared. So that is not obvious at all, how you cut it down from n over, my proposal was to, the total number of operations is n cubed. So if you do n rows in parallel, you cut it down to parallel time n squared. Unfortunately, despite the great attractiveness of Chansky, you would have to use maybe n to the 6 processors. So we see that this is not so. However, the theoretical study had a profound influence on the technology of parallelism, and let me mention one aspect of it, which also has to do a little bit with networks, namely in defining the connectivity, the various schemes for connectivity within these parallel computers. So if you have n processors, such as 10,000 processors, you want all of them to share somehow. So you would say, yeah, we connect every pair of those. Well, 10,000 squared and so on, we are getting, somehow I always get stuck on the same number, 50 million lines. It's similar to the private versus public key. So 50 million lines of direct connection are impossible. So first of all, computer scientists invented networks that do it by stages and that are like n log n in size, and route the information very efficiently. And there are many proposals, and in the deepest aspects of that, very advanced work by Noga Alon and others, Sarnak, Lubotsky, and Phillips entered into it, constructing very, very efficient networks for tasks such as that. Also, not just Noga, V.Milman as well, of course, the first paper. And Margulis, yes.
Okay.
Thank you.
It's okay not to mention names, but when people are here.
Yeah. Thank you. Thank you. You have to put that down to the fact that, you know, I'm sort of immersed in, I think by now we have mentioned everybody, and really thank you. I mean, this is unbelievably beautiful. Unbelievably beautiful, unbelievably beautiful work. So, and then just a final word about distributed systems. Distributed systems are something like the internet. The parallel computers are so-called strongly coupled. The whole parallel computer is in the same room. I mean, with the advance of technology, it may be in one shoebox, with a network which connects all components and so on. The distributed systems are worldwide distributed, and there are various things you want to do, especially in the area of protocols, where they do have to cooperate in various ways. And there are sophisticated algorithms that permit that, and protocols, again, randomization is very heavily used. That is a whole field in itself. Sometimes large distributed systems also act as almost a global parallel computer. So, for example, the factorization I spoke of a 140-digit number by use of the the general algebraic number field sieve method. That was done on, I think, several thousand computers working cooperatively as some kind of a distributed system. That is but one example, but maybe let me come back to the question of the internet and the large databases. Those very large databases are already distributed because each university has home pages and data about the people at that university, etc., etc. Sometimes you get a page from some central server. Sometimes you go directly or you are being sent there, and there are issues of how to define and manage and what algorithms govern and make these distributed, say, database systems possible. Now, that is going to be more or less the end of my introduction. There are things which I have left out, obviously, for example, computational geometry, computer graphics related to computational geometry, and of course many other fields, computational algebra, number theory related to cryptography. The field is extremely wide, but as a bottom line, I want to say that this is a real success story that automatically, without any edict from above, young people at the time saw the challenge, rose to the challenge, had wonderful opportunities. It's always to be, when you are one of the early people in the field, there are gold mines or gold veins to be discovered, whereas later generations have to work much harder to get things which are in many instances much less dramatic and fundamental. So there are also drawbacks of being an early person. A certain humorist, Saki, said, the early Christians got the fattest lions. So the people who chose those careers very often, certainly in the 60s, met with something between indifference and hostility within their academic, say, math departments. But that is really, I mean, these are small details which don't matter at all in the large picture. That is thus far. Now, what is your pleasure? Would you like to us to start with maybe some preliminary remarks on discrete mathematics and then open it for general discussion, or should we have some general discussion right away and then move for a change of pace to discrete mathematics?
Okay, and there's a J.
Second choice, okay.
Some talks were not completely conclusive with the seminar. For example, Zakharov didn't explain the major part of his talk concerning integration proof. If you can say a couple of words and then we can discuss it.
Okay, so we can do that. I would call upon everybody to be brief. Maybe I have already transgressed, but where is Zakharov? So by popular demand of one person.
Please.
I'm sorry because I'm totally unprepared, so maybe
Do you need some transparency?
Right. Yes. Right, so it is not so easy to talk about these things because for natural reasons we still have to get to Tel Aviv tonight. Yeah. I have to be brief, but yep, it's okay. So, but actually, what I wanted, well, I don't even have my slides here with me. Actually, why don't we postpone this short lecture? I will go and bring my slides from the suitcase, and we'll be back. And meanwhile, you will do something else.
Okay, but leave this here. All right. The shortest and best understood talk words in this conference.
I would like to invite.
Okay. So anybody who speaks maybe make use of the microphone. These were yours.
Yes, but I just would like to have short, brief idea of what you said in the talk, that this possibility to transfer information from A to B, to transfer information from A to B, says that A is able to prove to B that he sent and to prove to C that he did not send. You said this just, but just idea of such both possibility in the same place.
Okay. So that's a wonderful question, obviously planted by me. If we have time, I'll tell you a joke about planted questions. But we don't.
Let's start with a joke.
You want me to start with a joke? Okay. So I'll start with a joke. Also, of course, into the microphone. This I've heard as a true story from my brother who used to teach at Oxford University before he transferred to Jerusalem. So they have debating clubs where there are also lectures and then there are discussions. So somebody was invited to give a talk at one of those clubs, and he arranged with a friend 2 questions or a number of questions. He gave his lecture, and then who has any question? This guy raises his hand as a question. The speaker gives him a devastating answer. Everybody laughs. Another question, yes, I have another question. He didn't see, which way it goes. The same thing, he's being absolutely decimated. Everybody laughs. So he became a little bit sore, and he said, George, I don't quite remember, what was the 3rd question we agreed upon? Okay, so now let me describe how do you do deniable authentication. And these are those mind games. As I said also about internet and routing and so on, it's not just a question of analyzing a mathematical situation, which like in nature is forced upon you. You can exercise your inventiveness and hopefully make it easy. So here we have the sender and the receiver. The sender and the receiver. And the sender sends in the clear a message. It could be encrypted, but this is not essential. This is not essential to what we are saying. Now, the sender has a public key because the way he identifies himself or herself, there is a public key K of S. And of course, the sender also has a private key. And all those public and private keys are in the, no, not the private, the public keys are in the directory. Now, when the message is received, the receiver sends a question about this message encrypted by this public key. Now, what is the question? The question is the following in our scheme. He sends an irreducible polynomial that he chose randomly, say irreducible polynomial over the field F2, and what he wants to have in return, the message is of course a sequence of bits, so say 100,000 bits. It can be viewed as a polynomial of degree 100,000. So the return is going to be m mod this. The question is really a polynomial. M mod f. How does S know f? Because it was able to decrypt by use of the private key. So this is some polynomial g. F, say, is a polynomial of degree 200. Now, without knowing what the polynomial is, the probability of somebody giving the right residue is about 1/2 to the 200. The sender who is really doing this, knows that the only person who could send the correct answer with a very high probability, overwhelming high probability, or 200 we said, with an overwhelming high probability, must be the sender who has the private key. That's for him proof that M was sent by the sender. Now, how does deniability come in? Deniability, yes, please.
M is original message S to R. Yes?
Yes.
M was original message, and then it was transferred to G. Okay.
And then you perform the computation on it. The computation M mod F.
Mm-hmm.
And M mod F is a random irreducible polynomial chosen by R on that occasion. The fact that that whoever is out there is no face, there is no handshake. Yes? Whoever is out there was able to send this. That is proof that the original sender is actually S because he agreed to do it. How does deniability come into it? How does deniability come? Now you are getting to the highest order of mind games. The Inquisitor, of course, if he completely places himself instead of R, he's sitting there, then he is R, and he also gets a confirmation, like R. But the Inquisitor can do the following. He is sitting on the sidelines, but he is telling R to send C. So he is choosing F, encrypts it, and says to the receiver, when you get the message, send this ciphertext. Then, in that case, S will not be able to deny it because the Inquisitor will know that somebody decoded this C. So what S does, when he gets the question C, he asks for a proof of knowledge of the plaintext. I mentioned that as a new algorithm. So when he receives something encrypted by his public key, he can ask the sender to prove that he, the sender, in this case R becomes the sender, that R knows what is inside there. What is the significance of the fact that he has proved that he knows? First of all, there is a question, what does it mean to prove that you know? This sounds, knowledge in the sense of Descartes or Socrates. No. It has a very precise meaning, namely that actually R could reconstruct the contents, the hidden contents, on its own very quickly. Why does this now make the authentication deniable? For the following reason. The Inquisitor then comes and asks everybody to reveal their secret keys, so he even has DS. It doesn't matter. What S is going to say is, R, this exchange and the proof of knowledge did not happen between me, S, and R, the receiver, the voting booth. It rather happened between R and an accomplice. And what R really did was to decide about the M, decide about the F, tell his accomplice by another line, this is what the Inquisitor is listening to, but they have another line or prearrangement, tell him what F is, and then the correct thing is returned. So we have here a situation that everything that the Inquisitor saw could be simulated by R and an accomplice. And therefore S can say, I didn't do that. It's in a sense, if you can prove that there is somebody who can perfectly forge your signature, then you can disown your own checks. Because you say, here, there are maybe 10 people who can completely forge it. I didn't do it. So you see that we are talking here about fairly complicated mind games, but if you make the full analysis, you see that it is compelling. So on the one hand, you had, by a very simple protocol, the only part which is not simple is that when R is sending C, which is the encryption of the question to S, he, R, can prove knowledge of the ciphertext, of what, not ciphertext, of the plain text, of the secret inside. He can prove it, and then you have the question, how is that miracle achieved? In fact, the proof is very simple in a sense. I mean, at least it's very efficient, and in itself is also done completely in the clear. So any now R is the sender. Any sender for any encrypted message using our methods can prove the knowledge of the plain text. He does it in the clear, and yet absolutely nothing is being revealed. And all these are components of this solution. But altogether practical. So that's one of those situations where in the long run, the wonders of cryptography, so to speak, are going to be a help, you know, in real privacy protection in certain certain situations. Okay, now I think we have Sasha.
Anyway,
Please.
I will just show you my last slides because the real reason why I didn't show them during my official talk was that they were designed, well, for discussion rather than for a talk.
So that's now okay.
Well, so, and this. And it's, as you can see, they're even arranged in the form of several theses. So, and more or less what I wanted and what I can say on the matter, it is already written on my slides. So I will just give a few comments. And the PNP problem, which is probably at the heart of the modern theoretical computer science, was discovered around 30 years ago. And of course, when mathematicians discover some problem which is obviously very important, they try to solve it. And if the problem is really important, then at least for some limited time, it resists any attempts to solve it, because if you solve important problem in 5 or 10 minutes, then no matter how important it is, it immediately ceases to be important, right? There were actually several lines of attack on this problem, and I have to skip some early attack on it. The point is that a similar problem, very similar in spirit problem, it existed in the pure computability theory, and it has what we would call now a trivial solution. It's a post problem, and it's maybe not trivial, but it has an easy solution. It's just a reformulation of this problem at a different level. So people were very enthusiastic about it, and they tried to solve it, and they tried to use some techniques which, as we would say now, which are relative-wise, and it turned out that they don't work, and some other techniques were discovered. And probably what people were trying to do during several last years, was to solve this problem using lower bounds for Boolean circuits. It is well known that there is an almost equivalent reformulation of this problem in terms of Boolean circuits. Boolean circuits are just very simple gadgets. They really were used at least at early stages of technology for designing computers, and we simply have to prove that some very trivial thing can compute some very easy function. So it comes to very easy things, and it can be explained to any schoolboy in, I don't know, in half an hour. Nonetheless, the progress was very limited, right? Well, this thesis Okay, it can be discussed and.
So people are curious about the first line, feasible proofs.
Feasible proofs is actually there is some confusion about it because for the purpose of this short
Give us some idea.
But I'm going to give you a definition of natural proof. They have
Right. During my talk, I called feasible proofs as proofs in one or another logical system, which are feasible in what mathematical logicians would call it feasible. Today, I would like to combine feasible proofs are just proofs which use some limited means. Okay, I will explain later what I mean. So, and right. So enough said about this. This thing. So, and this is what I already said. The only thing I still have to add is that also this approach has not worked so far, just to prove lower bounds for Boolean circuits, which is an easy looking and combinatorial task. Still, there is a number of strong partial results about it, which somehow helped us to understand things better, and I think, and that's the point which I would like to propose also for our discussion, is that when we meet such a situation, when we have a sufficiently many results proved with this or that machinery, it is always helpful to look at the independence of the problem we are trying to solve, at least from this limited set of methods. It is, in my personal opinion, well, it's discussion session. In my personal opinion, it is not very important whether we will be able to prove independence or we will not be able to do it. What is important is that it's no matter what we are going to do here, it really advances our understanding of this problem. And good. Absolutely.
In the case that what you propose is to define a certain limited logic.
It is defined.
Well, let's see. And a limited logic, and to show that within this limited logical system, the question whether P is equal to NP is independent?
Yes.
That's what
Yes, absolutely.
So what is that limited logic?
Right.
Stronger or weaker?
I can actually answer. Well, so far I can answer all the questions, right? Like PNP problem, which resists all the attack. I still can also do it. And so far, these limited means, they mean two things. The first thing was already discussed during my talk, which is simply first-order theory or propositional proof systems which I discussed, and we are interested in short propositional proofs. So these are things feasible in a logical sense. So polynomial. All right, there are actually some catches here. Polynomial, well, if you're familiar with some details here, then polynomial means polynomial not in n, but in the number of input strings to the n. Right, and why it is natural and important, it is exactly explained by the chain of results we already have. Because, first of all, and there is also, there is... Sorry? No. N is the number of variables. 2 to the n is the number of inputs, but in fact, in many respects, it is more logical to look at these things exactly in the parameter you are talking about. But it's okay. Let it be to the n anyway. So, and natural proofs is something which we developed, and we try to approach this problem from a slightly different side. Namely, right, we forgot about logics. Well, I mean for a moment. And we simply look at the known proofs and try to see what they have in common. And it turned out that it is possible to distill several simple properties. Well, actually, there are 3 properties. First of all, okay, so it's maybe a little bit technical for our discussion, but still there are several properties, one combinatorial and one computational, but they are very natural, and we thoroughly checked that all known results they really fill in this framework. And it turned out that even in this framework, we already can prove non-trivial things about independence. Namely, and this is actually what is the most interesting, I think, about all this, is that here, quite surprisingly, at least for myself, we entered quite a different world, namely the world Mike Rabin was talking about. Namely, in order to prove independence in this, as long as natural proofs are concerned, we cannot do it unconditionally. We have to use some assumptions, well, like Avi was talking and Michael was talking, so... Right. There's no natural proof? Absolutely, yes, absolutely. Sorry. Right. Okay, so it is the most difficult business the most difficult task in all this business is to calculate the parity of negations you are using, right? You try to prove that something cannot prove that something cannot prove. But anyway, good. I think something like this. So it was something absolutely amazing because look at this thing. You are trying to prove that P is not equal to NP. You are trying to prove that some algorithms do not exist, right? And we are going to show that it cannot be proved. But in order to show that it cannot be proved, you have to use the same assumption. It goes exactly the opposite way around, right? So we would think that in order to show independence of some A, right, it's a sort of negation. You have to use the opposite assumption to A, and here you use the same assumption. It was really strange, and yeah, and right, and actually I think I will explain this, and this will be just the thing I want to say, because it is actually an illustration to the point I already made. So no matter whether it will lead us, it leads us to some understanding. And here is the understanding. Okay, there is a strong pseudo-random generator, Goldwasser, Goldrach, and Mikeli generator, and we can think of it as a generator which constructs pseudo-random Boolean function. It is a Boolean function, an algorithmic task, which on the one hand looks like a random one, and on the other hand, it can be easily computed. So, and the informal message which is conveyed by this stuff, and I do expect and I hope that there will be more messages like this, is this: look, you are going to show that there are no polynomial time algorithms for NP problems, right? And no polynomial size circuits. Let me put it like this. But here is some collection, some bunch of Boolean functions, which by definition look very random, like those which come from factoring or from something like that. They look very random. So if you conceive of some arguments, then just think of how are your arguments going to refute exactly this image of this generator. So, and I think that's about it what I was going to say. I'm sorry if it was not very intelligent. It is. I was not prepared.
Thank you very much. So maybe we'll have some reactions in general to computer science, theoretical computer science. I must say that I forgot one very important slide here. It's just going to take a second, but it is really very important. So we had that sequence of developments. First of all, theoretical computer science as the mathematical study of the process of computation. Then we had theoretical and also applied theoretical computer science, constructing algorithms, efficient algorithms, dealing with various problems of great practical importance. Now, the thing I forgot is the outreach, and that is again in the spirit of what Rafi was saying. So now it turns out that the methodologies, not now, in the past decade, that the methodologies have a bearing on brain research, not the actual physiology, but trying to understand how the brain does things. Outreach to computational biology in various forms. and outreach to quantum computations. And for example, Peter Shor couldn't have done what he did in constructing or proposing the quantum computation of factorization without a real understanding of the algorithms like Fourier transform and other things that he is implementing, and index calculations and so on, that he is implementing by use or hopes to implement by use of the quantum computer. And these are just a few examples. So within the university, and that's a case which we also made at Harvard for the development of computer science, within the university, not just university, in intellectual life, theoretical computer science has an outreach to many other topics. Methodologies from computer science can be used in literature and historical research and so on. So it's becoming ever wider, maybe wilder, but also more interesting. So I forgot that. Here it is. I invite comments of any sort.
I was just wondering if it would not be useful to hear first some short discussion of discrete mathematics, because otherwise we have no time.
Okay, definitely. Who? Lazzi. Please. One of us, maybe this should be closed.
Maybe I'll take this.
Yeah, take this one.
So,
is it open now? Yeah.
yes.
Please.
So what?
And you have here.
I know. I don't want to be that technical. What I thought of commenting on is that discrete math here is sort of bunched together with theoretical computer science, and my first thought was that this is really doing some injustice to the field, because discrete math is a branch of mathematics, and there are outstanding people in discrete mathematics who never think about computing and so on. My second thought was, on the other hand, that that's actually a very good thing for the subject, because we are sitting here with computer scientists, or I don't know where I count myself, but it's one culture in some sense. We understand each other better than, unfortunately, we understand each other with some of the pure mathematicians. And I think it's a little bit similar situation, like, people in analysis don't mind being put together with theoretical physicists. It's really a very closely tied subject. And this brings me back to the question of that Avi raised at the end of the previous discussion session, because when I started out as a discrete mathematician, and graphs theory and extreme graphs and all these sort of things, and then when I just first went to the United States in 72, 73, I learned about computational complexity theory. And it was immediately clear that this theory gives a lot of information about the kind of questions I was thinking about. Like, and let me add here one idea to Avi's question. So Avi suggested that if we look at some notion or concept, we should ask, can this be efficiently computed, or how efficiently can be computed? And that question will lead us to, in many cases, to deep structural understanding of the subject. Now, there's another thing here which is called under the probably not very fortunate name of non-determinism in computing. What it means is, I would say, provability and refutability. So if we claim some problem, how easy it is to give a certificate, some property, that whether you have a certificate that it's there or a certificate that it's not there. Like if you pick a number, how easy it is to certify that it's a composite number? Well, it's obvious. You just give a factorization. Is it easy to certify that it's a prime? Well, as it turns out, you can do it, but it's much trickier. You have to basically exhibit a primitive root modulo this number. And it turned out that in discrete math, there were some basic questions which people were trying to solve, like, given a graph, does it have a perfect matching, a set of edges which matches up all the nodes? And there was a beautiful answer to this in terms of Tut's that has a basic characterization of that. And then there's another question, does it have a Hamilton cycle, a cycle which goes through all the nodes? And it's a very similar question. It's pictures almost look like the same, but that turned out to be much more difficult. And computational complexity theory all of a sudden gave an explanation of this. One of these was in P, and the other one was NP complete. So if we assume that P is not equal to NP, this hypothesis, then there is a clear explanation of why we had so much success in answering one of the questions and why the other question was so difficult. And that's not an isolated example. For this, it's enough to assume that NP is not equal to co-NP. And it turned out that for the next decade or so, there was a big movement of trying to understand all sorts of questions in discrete math. In this, just asking these two questions: is it easily computable, or is it easily refutable, or provable, or certifiable? And in both cases, it turned out to be extremely. It led to very, very results which go way beyond the just graph theory and discrete math. As an example, you can look at the question of whether linear programming, which is another very basic question in mathematics, given a system of linear inequalities, is it solvable? And it turned out to be that the fact that this is in both NP and co-NP, in other words, it's provable and refutable, it goes back to classical theorems from the last century by Fourier and Farkas. But it was not known at that time whether it's polynomial time solvable. And then that was when the Kachian algorithm became known. It, of course, as everything, it had various predecessors, but and then a little bit later on, that sort of trouble with the Kachian algorithm. It was very inefficient. So one asked, can you do it efficiently, real world efficiently? And then Karmarkar's algorithm was discovered. And now not only is this Karmarkar algorithm the core of many fantastic programs that solve systems of inequalities with millions of variables and millions of constraints, huge things. But also it became the core of a very interesting development on the theory of convex bodies by Nesterov and Nemirovsky, which is algorithmically motivated, but it's a structural study of convexity, and it, as far as I can see it, it brings in a new aspect, a new way of looking at geometric properties of convex bodies. So all in all, I think that to be packaged together with theoretical computer science means that discrete mathematics is in the happy state that it has an application area which feeds exciting questions, and not only questions, deep insights into the field. Now, of course, on the third thought, the third side of the coin is that there is a lot of questions in real world which are discrete, sort of by at least have a very heavy discrete element. Protein folding was mentioned here. Clearly, the basic question is you have an entirely discrete object with just a sequence of amino acids. And now, how do you predict what it will do? I mean, it will curl up, and it will act in very strange ways. It can be a venom of a snake, or it can be an enzyme that helps your digestion, and lots of other things. So how does it happen, and what makes it happen? And of course the DNA and so on. Again, we are talking here about theoretical physics. Probably if you go to some other group of people, then they will call they will be talking about entirely different type of theoretical physics, which is much more discrete in nature, like statistical mechanics or other areas, Feynman graphs, and so on. So I think to conclude is that the third aspect of discrete math is that there is a lot of discreteness out there, and I think it's a little bit of a cultural thing. I will try to talk a little bit more about this in my talk, so I don't want to tell anything that I will repeat, but it's cultural, and I think it will be useful if people will be able to integrate this both sides.
Thank you very much. Before I call on Noga, I want to take issue with the question whether non-determinism is appropriate or not appropriate name. I think it's a very appropriate name. So Scott and I introduced it into computation. And now, you know, Shakespeare said, what is there in a name and so on. I think that part of its success was because the name was catchy. I mean, it is a fundamental concept, of course, which later on came up in NP, etc. But for example, we had to distinguish it very sharply from a probabilistic system. So, and that brings it is really non-deterministic in that sense. But that's just a historical comment. Noga, another discrete person.
Yeah. Discrete. I'll try to talk discretely here. So, yeah, I guess Lassie said almost everything I wanted to say about the connection between discrete mathematics and computer science. It's kind of obvious that theoretical computer science is one of the main reasons maybe for a lot of the development of discrete mathematics in, let's say, the last 20 years, and some of the reasons we heard now. I wanted to mention or to add two more points. So one is the connection between discrete mathematics and probability. So another thing which I think is more or less evident is that probability is one of the big things that happened in discrete mathematics in the last 20 years, maybe. I mean, it started before that, but it's mostly evident in recent years. And this is a connection, again, that goes, like in theoretical computer science, it goes both ways. So there are combinatorial methods that actually give new results in probability, like if you look at proofs of correlation inequalities, FKG type things, or things used in percolation. These are definitely combinatorial in nature, and yet they give results in probability. And of course, in the other way, there is what is called the probabilistic method. So things that started with Erdős and probably also with Shannon, where I think the most striking examples are when we use probabilistic reasoning to prove totally deterministic statements. And that exists in other fields as well, but in discrete mathematics, it's probably more than in other areas. And then, of course, there are also some subjects that are in between, like if you look at the study of random graphs or random objects, or if you look at percolation, sometimes it's difficult to even say if this is a part of combinatorics or part of probability or something in between. So definitely this connection is a very important connection, and I think it will keep being so. Now, one more maybe unrelated topics that I wanted to mention, and we touched upon this on Friday also, and this again is not something that exists only in discrete mathematics, but it exists in pure mathematics as well. and it's connected to computer science, and that's the issue of computer-assisted proofs. So again, I think that they appear more in discrete mathematics, but they appear in other parts of mathematics as well. And what I mean here is not proofs where you gain some intuition by doing computer experiments, which is also very important. But I mean really proofs that even after you found the proof, we at the moment do not know to check that it's valid without using computers. So still we cannot write the proof in a way that we can then read it and check it without using a computer. And there are more and more examples like these. And I guess it's more or less a safe prediction, although, of course, different people may think differently, but it's reasonable to expect that we would have more and more proofs of this type, just because the tool is there. I mean, we can test, so maybe it's not so good, right? So sometimes, indeed, when we prove, say, a result in pure mathematics, we want to see what is a reason. And a reason usually means a short proof, or a proof that we can understand and we can read. But inevitably, it seems that there are short statements that have only long proofs. I mean, there are also some formal ways to prove statements of this type. And it is very natural, or natural is a bad word, we say, but it is reasonable, let's say, to believe that indeed, since the tool is there, then we are likely to use it. So there would be just these proofs that we first do all the clever things, and then we have to still do some computations that we have to do in 10 hours of computer time, and then we'll just do it. So I think it will be interesting also to hear what people think about this. I mean, are these proofs desirable in pure mathematics, let's say? Should we avoid them? Would they exist in the future more, or would they vanish?
Okay. Fine. Maybe we'll come back to the last extremely interesting point of Norgaard's. For example, the work of Zeilberger in proving various identities, say about binomial coefficients and other mathematical functions. But I would like now to open, we have heard about computer science, theoretical computer science, discrete mathematics. Any comments? Yes?
I just want to make a short proof about computer-assisted proofs. So, in mathematics also there are...
Is it done? Okay.
I don't think so. So just go
Okay.
So I just wanted to say that in mathematics also there are certain results which are not very conceptual, which require a lot of steps, I don't know, 10 steps that have to be verified. And are they satisfactory? I think the answer is either the problem is not very interesting and the result will kind of disappear, or if it is very important for the development of a certain field, there will be other proofs later on, which will be more conceptual. So I think it's the same probably applies to this issue of computer-assisted proofs.
Any more? Yes, Rafi.
Yeah. The question is, what do you think are the challenges actually that face you? I mean, you mentioned biological or brain computations. There are possibly completely different ways of processing information, or computing if you wish, which don't follow the standard model that you have. They will promote challenges. How much exploration is happening in that direction? I really don't know much about the field. I'm basically asking.
Well, it shouldn't really be a dialogue, say, between us, because we want to open it. So just one word. So quantum computing, for example, is another way of doing computation. And it's wide open. There could be other. And with respect to brain computation, that of course comes to artificial intelligence, which on purpose, out of politeness, I didn't mention. But there is really a question we can do, maybe eventually we will do artificial intelligence, in one of two ways. Maybe we'll really understand how the brain solves problems, and your question how does this piece of meat remember and know that we don't know Clinton's telephone number. We may find other ways of doing it, or we may understand how the brain does it, or both. And nobody can say this is too much in the future, but I'm sure it will be dealt with. Yes?
My feeling is that there is a tendency to separate computer science from pure mathematics, and to call it a separate arena of activity. And maybe the reason of not able to attack properly question of such NP is not equal to P is because of this separation, because before maybe you ask the question very not in the correct stage of technology, of mathematical technology. For instance, I don't know anything about it either, but the Weyl conjecture in mathematics needed, a great framework of all the Grothendieck work in constructions before someone could even ask the question properly. Maybe you don't ask the question properly, and you have to develop some correct framework to ask the question in this framework and then answer it. And this is a pure mathematics, and you need to be a great mathematician in order to do it. And my feeling is that computer science is very down to earth, stayed very down to earth, stayed with all these basic tools of the 9th grade mathematics, very bright minds, but very low-level tools, and maybe this is one of the drawbacks of this arena, I think.
Okay, any more? Anyone would like to comment on the last comment, or raise other issues?
The future will prove this very soon.
But I want to do computer science in this one.
But it's.
You want to say something about the last point? Okay.
There is this
First Avi and then Sasha.
Maybe.
No.
Yeah, I just, I can say something. I also felt that maybe your answer to Rafi was a little short, so maybe.
Okay,
but,
please.
Yeah, so I mean, you may be totally right, and the reason we didn't solve it is we didn't use sufficiently high mathematics. I mean, the P versus NP problem, and in fact, if you really followed what Sasha was saying in his proposal, he just mentioned exactly this. I mean, this natural proofs, what he called natural proofs, or the fragments of piano arithmetic that he defined, just capture the methods that we have used so far in order to prove lower bounds on Boolean circuits. They got us to the place where we stand. And if indeed the question is independent of the theories, it means we need tools that are, use heavier mathematics, at least in the logical sense. Okay, so that's why we invite all of you to work on these problems and use topology and dynamics and geometry and what have you. That's on this point. I mean, I think that's probably, the same statement may be said about the Riemann hypothesis or Poincaré conjecture. Maybe it's not solved yet because it, you didn't use the right tools. It's sort of an obvious statement about any problem that is still unsolved. I think it's really interesting the path that was taken by Aita and Razborov and others to actually, self-interrogate ourselves and not just say, okay, let's invent more tools and try to attack it from this, not just trying to have more ideas, but also to introspect the methods we have used so far, to encapsulate them into a formal system and argue about this, whether it's sufficient or not. I don't know if this was done about the other major open questions.
why you always say that this is the faculty of mathematics and computer science, and not the faculty of mathematics and number theory.
I don't care about names. Okay. I don't care. I don't care about. I think that yeah, this is besides the point. If you equate computer science with 9th grade mathematics, I think you are a little short in knowledge. But anyway, I'm yeah. Let me just say, I mean, just a couple of words. I think this topic probably deserves a discussion of its own. But the question was that there are other modes and models of computing, and we have our Turing machine. Do we, go somewhere else? And the answer is a huge yes. I think that we now understand that we have tools to argue about models of computation, to define them, to study their strength and their connections to other models. In fact, Michael was mentioning some of them when he talked about distributed computing, parallel computing, and it is definitely, and quantum computing, and it's definitely true also when about some of the people that are trying to understand the brain from a computational point of view. I think that's it's extremely interesting when people have theories about memory, about association, about things we do, visual system, about things we do, to really try to understand whether we can build a model of the brain concept, computational, not physiological or psychological, but computational, and say, oh, here is a computational model, and look, it can do these things. And I think there's really interesting work in this direction. Valiant is one of the pioneers of that, and yes, we are, some of us are getting into that research, sure.
Sasha wanted.
Wait, I want to change maybe a little bit.
For $5?
Huh? No. There was a question here, Alain. You're sure?
I can ask if I may.
Sasha, is what you wanted to say covered by Avi?
Actually, I just tried a couple of short sentences. The theoretical computer science is not something unique. So, and people there have different opinions. I also respond to the last points. So, and one can get an experience like you are describing, but believe me, there are many people, and you can count on myself, for example, who really share these 2 points, that mathematics, that theoretical computer science should not be separated from mathematics, and that whenever we feel that new mathematical, deep mathematical ideas are needed for our problems, we immediately bring them in and we learn new things, and there are many examples. So that's the only thing I wanted to add.
Okay. John.
So I'd just like to say a little bit about the perspective of an analyst here, which is that I come here and I see some sort of Tower of Babel, that you have various communities that should be talking very directly to each other and should be able to understand each other, and there's a basic ability, and I think we shouldn't have too high opinions of ourselves, that these confusions arise not at some high level but at some extremely basic level. And just as an example of the failure of the analyst to communicate this clearly, many people believe that what the Fourier analysts do is they do continuous arguments. But the whole of modern Fourier analysis is based on the fact that continuous arguments fail. So what we do is discrete arguments. And these discrete arguments, of course, have deep analogs in theoretical computer science. This is a whole area that deserves to be studied.
Perhaps only one word about something which was said here about computing supporting solving problem with computer assisted proofs. I just think it depends on questions. For some question which you really, the most important thing to know answer, Riemannian hypothesis, for example, it absolutely no matter how you come to, if you need 100 or more hours of computing work, do this. But for some other questions, the main point is in different place. And very often, exactly problem where point is in different place, solved with computing assistance. And this is where stay this contradiction. So for some problem, you should know answer. For some, you want to understand what structure and ideas stay behind to simple problem, not to be able to have simple answer. And here, computing assistant proof is just, to have record, to put, but not.
Well, the question is, just very short. But suppose that these questions do not have proofs that are not computer assisted. So suppose that the only possible proof is...
It's always in the system of given structure you already have in mathematics. It is always, your answer is always in the special structure of existing, called this axiom of structure you discover, so you need to discover next structure. It is only in the given framework, whatever you said is correct.
Okay. Any, Alain? Please.
Just a question to what you were saying. You know, in your talk, you mentioned the permanence and the determinants and so on, but I sort of didn't get the details of the reformulation of the question. So could you give some detail here? I mean, just formulate it in such a way that.
I can put the slide again if
yeah.
make you work from the
right.
problem. I mean,
no, just to make it clear that what the problem means. I mean, otherwise I don't understand it. I mean,
it's one of these mathematical definitions that everybody is familiar with, so I don't have to say anything. I just put it again, and you can. Let me find a minute to find it. You can. Yeah, I mean, people want to discuss.
Maybe just a word to this question. I think that's, I mean, in connection with good questions and bad questions and not... No, I'm pointing on the chair in front of you. So I think that there is some virtue in discovering questions where you sort of all of a sudden stand up and say, but how come we don't know the answer to? I mean, this is one of those questions. I mean, P is not equal to NP. Of course, you couldn't have asked this question 100 years ago. But whether the determinant can be specialized to get the permanent.
Why is the permanent a nice thing?
Oh, I'll tell you.
Well, that's a nasty thing, exactly. That's the point. But
what is the... Yeah, okay. Yeah, so, oops, it's not this. Well, I'll tell you, that's almost, yeah. Well, basically, the fact that the permanent is an interesting function is a non-trivial discovery of variant. And so in some sense, it's a complete problem like the NP complete problems, only harder. But the nice thing about it is it's not, something like satisfiability where you are talking about Boolean formulas which are ugly objects and they are discrete and you understand that you don't understand what they are. Whereas here you are talking about, a polynomial that's so nice and looks so much like the determinant. So that's...
You didn't say exactly what was the operations.
Okay. Oh, here it is. There are no. The nice thing is there are no operations.
Well, you have to change the degree.
Yeah, just changing the degree. Well, I mean, it looks pretty embarrassing, especially since I had it. Okay, you give me a minute.
Okay. So don't...
Oh, I can just say. Amazing. I can just say. Yeah, okay. I will say, yeah. I don't know why I'm... Yeah. Okay, so in general, what you are interested in is to take a projection, takes one polynomial in some, let's say, real space or over any field, fix a field that you like. Okay, we'll take a polynomial with many variables over this field. Projection just means that we look how this polynomial looks like in an affine subspace of smaller dimension. That's it. And of course, there is another polynomial of fewer variables, which is a dimension that you went down to, right? So the 2 points I made were A is that the determinant, and in fact, every efficiently computable polynomial, not just the determinant, is a polynomial projection of the permanent, of the maybe square. That's Valiant's theorem. Okay, in this sense, the permanent is complete. It's an amazing thing in its own. The permanent is complete in this very simple sense of projection to a affine subspace that's not much smaller than what you start with. Okay, and the other direction, the permanent is also a restriction of the determinant. But there, the only proof we have so far is that it's exponential. the degree is exponentially higher. Whether you can do it in a polynomial, just with a polynomial increase, is essentially equivalent. It's really essentially equivalent to the P versus NP question. Which means, well, let's say if the field is a finite field, then basically it's equivalent up to notions whether Turing machines are different than circuits. But yeah, it is equivalent. And the reason it's equivalent, and not just, implies P different than NP, is that not only the permanent is complete in one sense that I explained, but the determinant is also complete in another sense. Everything you have a short formula for, you can encode as a small determinant. So it's equivalent. So you can forget about computation and really work on this. Yeah.
Yeah, only it's similar to work on any other NP-complete program, only that this looks more...
It looks more appealing. Maybe you'll give up because the permanent is really as ugly as Boolean formula. But nevertheless, there is less computation in the definition.
Maybe I'll make a further remark on that, and on your remark. There is no doubt that the P versus NP, whether they are equal or not, is a centrally important problem with very far-reaching consequences either way. And in relation, or when it comes to our failure, to settle it, I'm a little bit in sympathy with you, not about the elementary nature of theoretical computer science, but one of two things could happen. Either somebody will find an efficient algorithm for NP-complete problems, so this is going to be probably very, very clever and involve new ideas in the same way that, say, Karmakar was a departure and Kachin before, but mainly Karmakar was a departure from what was done before, and a new insight, and that may happen here. But we are probably not ready for a negative result, and part of the difficulty is that the problem is sort of too particular. So if you try to take any of these particular questions, such as satisfiability or three-colorability or Hamiltonian circuit, they are sort of grainy. And what you would require would be some higher level of abstraction. So, for example, the problems of topology, of what was called combinatorial topology, were fairly inaccessible until there was a systematic introduction of various associated invariants, groups of various kinds, homomorphisms and other and isomorphisms between groups and so on. And we are lacking that kind of structure in the problem at hand and in computation in general. Computation seems to be sort of particular, dependent in some sense on models, on machines, and so on. So maybe the projections, I doubt it, maybe these algebraic projections will be the sufficiently high level abstraction which is going to lead us, say, to a P not equal to NP proof. But we are probably far away, and because we are far away, it's also senseless to try to predict. I would say that if the problem is solved in the direction of P equals NP, it could happen in the coming decade. I would be much less willing to make a prediction if P is not equal to NP when a proof will actually arise.
What about independence?
I don't believe in that. I simply don't believe in that.
They cannot be independent. No, it cannot be proven to be independent.
Certainly not.
No, I mean, if you have a proof that it's independent, then it includes the statement that there is no polynomial time algorithm for Hamilton's cycle, which, because the point is that that's a recognizable object, at least if you define polynomial time properly.
Not quite, because there may be a polynomial time algorithm and you won't be able to prove that it doesn't.
Yes, but I say that I assume that an algorithm I mean, you can formalize polynomial time by bounded depths of cycles, and then there is a formal definition, and if you use this formal definition, then it's recognizable.
But I would say that we shouldn't go far afield. By the same token, if you consider the difficulty of the question at the time it took to settle it, you might claim that Fermat's problem, the large Fermat theorem is independent, and similarly for the Riemann hypothesis, I don't believe that to be the case.
Well, Fermat's last theorem really cannot be independent, right? Because if it's not true, you can write down.
Yes, but it could be true. It could be provable. Yeah, it could be true without being provable.
Yes.
So, and we know it's true. So now we know. Now we know it's true. I want to get some other reactions. And by the way, our time is running very short. But I invite, before Latzi, any other comments on this? Or does anybody want to relate what we are discussing now to Rafi's discussion in the morning? So you'll have the last word. A heavy responsibility.
I wanted to mention an analogy that 2p equals np, and that's the questions say whether you can trisect an angle, which was raised in ancient times, and it was an entirely well-defined question, and the answer was suspected to be no, but of course there were just no means to prove this. And then mathematics developed, and real numbers were invented, and algebra was invented, and eventually now you can actually prove it in a, like a special, you give a special class to a high school, you can essentially give the proof that an angle cannot be trisected. So I believe that the situation is similar here.
I think that's a wonderful example. So I'm having the last word. It's a wonderful example in the following sense, that concepts which seem to have nothing to do with the question at hand, namely the degree of an algebraic extension over Q in this case, and the fact that the algebraic extensions by ruler and compass constructions have degree 2 to the n, and 3 happens not to divide 2 to the n. So the Greeks couldn't do it, Newton couldn't do it, and so on. But Gauss could do it.
He could see the 3 doesn't divide.
Yeah. Okay. Thank you very much.